Hi, I'm Jen Schachter with Tested.com. I recently worked with Adam on Project Egress, a collaboration between 40 makers from around the country. We built a replica of the Apollo 11 command module hatch for the Air and Space Museum. I worked really closely on this project with the Smithsonian Digitization Program Office, and I'm here today to talk to Vince Rossi, the head of the 3D program, about the work that they do here. Do you want to talk to me about what your office does?
Yeah, absolutely. So what our team does is we 3D scan Smithsonian objects, and we work for all the different museums. So when you think about the Smithsonian, you think about the exhibits, and what's on display. But what our team does is we 3D scan museum objects, sometimes on exhibit display, other times not. And we have this huge collection. So we have 19 museums, 9 research centers. We have 155 million objects, but less than 1% of those collection items can ever be on physical display. So what our team does is we'll 3D scan those objects, and then we can do all kinds of cool things, bring them back into the real world through 3D printing, load it on a VR, AR device, or just make it available online for school kids to play with and check out.
So this is a skeleton that was 3D scanned by your team in its entirety?
Yep, absolutely. So we 3D scanned all the bones, and this was a really cool story because we 3D scanned this object, and then we we made it available for the public to download. And to our surprise, a Japanese toy maker in Japan took that scan data and added articulated joints to the 3D scan data, and then shared it back to us. So it's that kind of a really cool thing that we wouldn't have expected to happen. Was made possible just by putting the data out there.
That's amazing. So all the scans that you take of different objects can be manipulated, and the data is all open source?
The data is not open source.
Okay.
It can't be used for commercial use, but any educational use is completely allowable, and you can definitely modify the data, mash it up, 3D print it, and do whatever you want pretty much.
That's amazing. So I heard an interesting stat, and correct me if I'm wrong on this, but 1% or less than 1% of the entire Smithsonian collection is actually on display?
Yes, that's pretty incredible, right? So we have 155 million objects spread across the 19 museums, but most of that stuff is in storage, and we just don't have the buildings to display 155 million objects. Now, some people could see that as kind of an access problem, right? Like, if you're a researcher, you can come to the Smithsonian, get behind the scenes, and see some of these things that are not on display. But the vast majority of humans on Earth, just don't get to see this stuff. So that's what really inspires our team, this challenge, for us to scan what's on exhibit display, but also to take our 3D scanning tools behind the scenes and basically unlock this collection using the technology of 3D scanning devices. So that's super inspiring and what really excites our team.
I love also that not only do people have access to it, but they can interact with it in a way that you wouldn't normally get to interact with a museum object or a historical artifact. So we were able to really intimately get to know the hatch, and people actually make pieces of machinery on their own. You said the hatch normally would be behind a vitrine plexi display, and no one would ever be able to touch it or measure it or any of those things. So people can take these files into their homes and learn about the thing and get to know it really well by having that 3D model and potentially printing it or viewing it in AR or VR.
Yeah. So again, that's what really excites us too. What people do with this data, bringing it back into their home, creating something on their own, creating a replica that maybe even sits on their desks or becomes this amazing Project Egress. That's super exciting. And then the other thing our team really does and gets excited about is once we scan a 3D model, so after we scan the Apollo command module hatch, we have that amazing object. Now we have that data that we have all these options, right? We could do AR, VR, give it to the public for 3D printing, but we also have the experts, the content expert, the person who has devoted his life to studying this object, and that's kind of a challenge we haven't fully figured out yet, but we're starting to work on that. How do we use that 3D model kind of as a scaffolding for storytelling, or as a way to allow people to investigate that object? So virtually, you start poking around on that 3D model on your internet-connected device, and then information pops up, right? This is information that would be hard to convey in the museum. If you think about the way exhibits are usually constructed, you have an object and then you have a little placard that tells you, in a few sentences what that object is. Now suddenly, if we're able to, touch different buttons within the command module, and we get, audio from the astronauts or videos popping up of the Saturn V rocket blasting off or other information, that would be a hard thing to do in gallery. But virtually, that's something that's pretty easy to do.
So this model is very familiar to me because we just recreated it. This was a scan that was done several years ago by your office of the entire command module, right?
Yeah, that's right. So that object, the command module, incredibly iconic. It was wrapped in this plexiglass vitrine. And if you were a little kid, you could come up to maybe like the opening of the hatch opening to like peek inside, but you really couldn't see inside. So our team was able to 3D scan the exterior and the interior of the command module, as well as the hatch. And that was just an amazing project. So we partnered with Autodesk, and we used basically all the tools that were part of our toolkit and collected just huge amounts of information. And we basically broke the Autodesk software, which is actually what they wanted. Like that's their team was looking for ways to like really just find, ways to innovate their technology. So by giving them huge amounts of data, they're able to improve their tools and give us this incredible 3D model.
So there were two different versions, right? There was LiDAR and photogrammetry?
Yeah, so there was LiDAR, photogrammetry, there was also structured light and laser line scanning, as well as another kind of different flavor of structured light. So we basically, again, we took all the tools we had. And the really challenging thing for that project is our physical bodies couldn't go inside the command module, so we had to design motion control systems that reached through the hatch opening, and we remote controlled the scanning devices from outside the command module.
Wow.
So lots of challenges and lots of fun too.
I imagine. I've heard too that because there's so much reflective material, that's a challenge for some of the scanning equipment.
Anything that's super reflective, a laser beam hits something that's really shiny, and it doesn't bounce back the way it would if you're scanning, say, a bone on a woolly mammoth. The time it takes for a laser beam to be emitted, hit the surface, and bounce back equates to a very precise measurement. That happens with some scanners 1 million times per second, which is just incredible. But if you're doing that on something really shiny, that laser hits the surface, kind of diffracts in all these unexpected ways, so you end up with lots of scanner noise. So our team definitely struggled with that, and we had to use a number of different tricks to kind of resolve those shiny issues.
So you're able to then stitch the data, both the surface geometry as well as sort of the skin and the colors and reflective properties of the object, and stitch those together into a fully functioning, pretty convincing 3D model.
Yeah, absolutely. And that's definitely where most of the work comes in. So we had 2 weeks on the ground scanning the command module, but then about 6 months processing the data. So that gives you an idea of the level of effort that goes into processing data sets that are this complex. And basically what we do is we borrow tools and technologies from other industries. So Hollywood, animation, medical industries, we basically cherry pick those solutions, because we're not engineers, we're not programmers, so we're end users. And what we're good at doing is kind of taking these solutions designed for other applications and kind of creating workflows that works for the museum.
Once the data is sort of processed, and I imagine it's compressed quite a bit, this is available on your site for people to then download. And what kind of things have people done with the files?
Well, so far we've seen a lot of really cool uses, and yeah, we make all the data available for download except for the highest resolution of data. So when we 3D scan something like the command module, we might have 200 gigabytes of raw data. So we're just, with internet or web servers, we're not able to serve up that data. But if someone requests it, we could make higher resolution data sets available. But we still make models that anyone can download. But the problem is, if we were to take that super high resolution data, I'd say 99% of people couldn't open it up. So that's also why we're not serving it up.
So we were able to take the data, and we worked with Andrew Barth, who then collected all of the original kind of, not raw data, but there were definitely still some artifacts and things that needed to be cleaned up. But it was one solid model. There were no separations between pieces of machinery. The model certainly wasn't able to articulate. He then took your scan data, in addition to drawings from the Smithsonian archives of the original hatch, and basically reverse engineered the entire thing to scale by each of its mechanical components.
Yeah, so that was just incredible. The level of effort that Andrew went through to create and to model every single component down to the screw, hundreds of different components derived from, like you said, the laser scan data, different technical drawings, is unbelievable. So we're super happy that, basically Andrew was like key to making this project happen. Without his work, I don't think we would have seen that build happening yesterday.
And all of those individual STL files and drawings are available online as well, so that people can make their own hatch at home at whatever scale.
Yeah, that's right, absolutely. So all that hard work that Andrew did, modeling off of our scan data, that entire data set, that entire package can be downloaded, and anyone can make their own one-to-one command module hatch.
So cool. And a couple people have, I think. We've seen a few
definitely.
3D printed versions at one-to-one scale and at half scale.
Yep, so I'm following that on social media, incredibly exciting. And I already talked to Andrew about the possibilities of doing this to the entire command module. So that might take some time, but that would be super cool if we could do that.
Did your team discover anything that hadn't been noticed before about the command module in the process of scanning it?
Yeah, so a few things happened. It was known that the astronauts had written a few notes inside the command module, but since you couldn't, it was encased in plexiglass, you couldn't get inside. We didn't have good documentation on what's inside, other than a few shots from outside the command module looking in through the hatch window. So with our team's 3D scans of the entire interior of the command module, we're able to reveal what the curator was calling astronaut graffiti. And that was basically, the astronauts talking to mission control, writing notes like on the different surfaces within the command module. In some cases, like taking calculations, doing math, and just kind of using it as like a scratch pad. So we have a complete documentation of all these astronaut notes that kind of came along with the scan data. So we didn't really discover that, but we kind of like revealed a new light and kind of exposed that to the public. So that was a really cool outcome of the 3D scan.
That's so awesome. I'd love to see a little bit of how this process works. Can you show us a demo?
Yeah, absolutely.
Great.
Let's check it out.
The command module is a much larger object, but the scanning process works the same for something smaller. I'm here with Meg, the Digitization Project Manager, to talk about how that process works. So Meg, this is a familiar object.
Right, so this is Adam Savage's replica Armstrong glove, the left glove, which is one of the first objects of the Armstrong suit that we 3D scanned. We released the left glove to the Kickstarter backers for the Reboot the Suit campaign, so I thought it would be a great marriage of the Smithsonian object and Adam's passions.
This is a very prized object of his. It was made by Ryan Nagata, and we're going to see how the process works on this glove and then possibly compare it to the original?
Yes.
Cool.
So the first process that we're going to demonstrate is the laser arm scanner, and we use this quite a bit for our projects. The anatomy of this scanner is pretty similar to a human arm in that it's got 3 articulated joints, like you've got your shoulder, elbow, wrist, and each one of them has an angular encoder that tells the scanner where it is in space. So you have an indication of where your scanner is in space, and then on the end we have a laser line probe, which projects a green laser line onto your object, and the camera picks up roughly 2,000 points in space on that line. And you scan by sweeping the line over the object, and then you begin to accumulate hundreds of thousands to millions of points that make up the surface of the object down to less than 1/10 of a millimeter accurate. So what you have here is this green laser is the laser line that it's actually picking up the points, and then the reddish crosshairs telling you how far away you should be. But you just start and sweep across the surface. So you can see the data starts to visualize on the screen as you're working, because this turntable is actually connected to the scanner. So the scanner knows where it is in space and where the object is in space.
So how long would a scan like this take, typically?
A scan of this glove would just be a couple hours. Probably even within 1 hour you can get the full exterior. If you wanted to do the interior, you'd probably do another hour. When we were scanning the full Armstrong suit, it took us, I think it was half a day to do the whole suit with this method.
Wow. Does the technology update and change at a pretty rapid pace?
Oh, yes. Yes.
So you have to do a lot
Very
to
rapidly.
stay on top of it.
Yeah, I think this is even a new version of this arm that we then had to get trained on. The new version actually picks up some color information too, and it has a different laser that reacts better with shiny surfaces. So you know how shiny surfaces are really an issue with 3D scanning. That stuff is actively being addressed by all of the companies, and we have to stay up to date with the new technology.
So it might have been easier to scan the hatch now than it was even 3 years
with
ago.
this arm it would have been even easier. Yeah.
So where do you get equipment like this? I mean, I couldn't just have this in my house, right?
Well, most of our equipment is donated through partnerships with companies like Autodesk and Faro, who donated the scan arm design that we're using.
Okay, and I imagine it's a pretty high-tech machine, so it would be an investment to have one at home.
Yeah, definitely. So this method is really great to capture high-resolution surface information, but then we bring in photogrammetry to map color on top of that.
So you're able to take the skin sort of and apply it over top of the geometry.
Yes.
Can we see that?
Yeah, absolutely.
Cool. We saw the ferro arm captures geometric data about an object. Now we're going to take a look at how photogrammetry can capture surface color and texture. Max, who's a 3D digitization specialist, is going to walk us through that process.
Yeah, so like you said, the laser arm captures really good surface detail. Photogrammetry, while it's versatile, it captures geometry as well. The surface detail isn't going to be as clean. What it excels in, though, is getting really good, accurate color information from the camera. So what we'll do is use the surface model from the laser scan and the texture from the photogrammetry to kind of marry the best parts of both processes.
The computer is able to take the flat images and apply them to the surface of the geometry that we've collected from the LiDAR.
The photogrammetry is making a geometry as well, so all you need to do is just line the geometry from the laser arm to the geometry of the photogrammetry, and then the texture from the photogrammetry will like easily overlay onto the laser scan.
Interesting.
So an object like this that you can easily get all the way around, you can kind of see all of it at one point. You might take it off this, put it in a different position to get coverage of like another element like the inside. This would take probably a day to shoot, longer to process. But an object like a space shuttle, for instance, or something larger than you, that might take a really long time, especially if it has like intricate areas. An object potentially more complicated in terms of surface detail and stuff at this scale could also take longer. It all just depends on, I guess, the intricacies and the size.
How long does an object like the space shuttle take to scan?
In total, it probably took about a month with 4 or 5 people working consistently, shooting photogrammetry. So we did 2 weeks all the way around on the outside, 2 weeks inside, just shooting kind of as much as we could. People were working on different sections of it, obviously, and that just collected like probably 80,000 photos, and it's going to take even longer to process.
So after this, you've got tens of thousands, maybe hundreds of thousands of images from both LiDAR and photogrammetry. What happens next?
So the next step would be pulling both the raw laser data and the raw photo data into separate programs, processing those into whatever resolvable mesh needs to be made. Then the next step would be putting the color from the photogrammetry onto the laser data. And at that point, we'd have a really high quality, both in terms of texture and surface detail mesh. And from that mesh, we can derive a host of different deliverables, models at different resolutions and scales for people's uses, be it 3D printing, AR, web support, research, it just depends.
So this is one example of something that was printed mainly using the ferro arm, the LiDAR scans.
Exactly. There's obviously no color information on this, so this is purely just from the geometry taken from the laser arm scan. And you can see even like where it's captured the stitching here, and just the different material surfaces, even in this quality and this material, are pretty well represented.
In contrast, this is a model that has had the photogrammetry data applied to it.
Exactly. It's a mesh that was made with a whole host of laser scan data, and the photogrammetry texture was projected onto it after the fact.
So these are 2 ways, but there's still one more process on how this is made.
So there's a third process called structured light scanning that does both of these, color and geometry, at the same time.
I'd love to take a look at that too, if we can.
Yeah, for sure.
So there's an additional process that's used to capture data. We've covered 2 of them. John, you're a program officer here. What's the third process?
Right, so I'm going to talk about structured light scanning. So we use a couple different structured light scanners. I'm going to go over one of the handheld ones we have. Meg talked about laser arm scanning that gets us really good geometry. Photogrammetry gets us geometry, but also really great color information. Structured light scanning gets us a mix of both worlds. So a structured light scanner that you might be familiar with is Microsoft Kinect. So how structured light scanners work is they project a pattern of light. So in the Microsoft Kinect example, that's an IR pattern. The scanner I'll be using is a blue light pattern. Then cameras read how that pattern deforms over a surface. If you include a color camera in that setup, then you can apply color information to that geometry.
So it seems on first glance that this is sort of a redundancy with the other two processes. Is there something different that this one's capturing that the others are missing?
It is redundant. We do like to get redundant data when we do capture of kind of like an iconic object that we get access to once, right? Like our time is not the important thing, it's the object and the object safety. So if we get access, we want to kind of throw everything we got at it and then process later. Also, the tool that we're using here, the handheld structured light scanner, it's very versatile. The laser arm scanner needs to be mounted to a particular point. It needs to be mounted to a table or a very sturdy tripod. Then it only has that kind of 2-meter reach. Photogrammetry has other restrictions. The handheld structured light scanner is essentially a 3D video camera. It takes between 1 to 16 3D frames per second and aligns them in real time. So I can literally just a magic wand, wave the tool around, and I'm going to be capturing data. So if there's any occlusions that I couldn't get with the other tools, or any kind of complicated surfaces that photogrammetry is not going to capture well and I can't reach with the laser arm, I can then capture with the structured light scanner. So
this gives you a lot more fluidity of motion for potentially less than ideal conditions, and also fills in the gaps that the other two processes couldn't capture.
Exactly. And at the end of the day, it's we'll take the data that we got from each different process, we'll run through paces, and then we'll evaluate it and then kind of pick the best data from each capture source and apply it to that final model. There's a handheld structured light scanner. We can see that it is it's projecting a fringe pattern onto the surface of the object, and then it's got 3 cameras that are reading how that pattern deforms over the surface. The really bright light you're seeing is actually a flash for the color camera, so we're going to capture color information. And we're capturing about 5 frames per second, and the software is aligning those frames to each other in real time. So again, you can imagine if there's a, for example, the woolly mammoth trying to get up top where the spine is, or in the command module kind of getting up top where there's like nooks and crannies. This is a really valuable tool.
So is this something that's more accessible potentially for someone to, say, purchase and have for home use, or?
I would recommend photogrammetry for anybody who wants to start out, and honestly for anybody who's looking to build a 3D digitization kit. Photogrammetry is a place to start. You can you can capture decent photogrammetry with your cell phone, plastic lens and a cell phone camera, and some like open source software. It's not going to be the best model, but it'll be something, and you can go from there. You improve your camera body, the lenses you use, and the different softwares available. You can really capture some great information. If you're going to look into getting actual scanning hardware, you're looking at thousands of dollars and up. Where again, photogrammetry, you can start out with a cell phone camera you already have and some free software.
So once all of this data is collected, the data set is massive, hundreds of thousands of files and gigabytes. What happens with all of the data afterwards? What's the post-processing?
So post-processing, each different capture tool has its own software that will process the data in for the most part. So we'll process the data out so we have some sort of geometry, some sort of mesh for that model. In photogrammetry's case and in the structured light case, we'll also apply the color information. And then we'll kind of evaluate each one of those 3 models, see if there's, for example, the laser arm scanner, we're probably going to use that information for geometry. But we'll look at that model and might be missing, let's say like in the armpit or somewhere that's occluded, we might be missing some information. Next, we'd probably go to the RTEC data set, see if we have that information there. If we don't have the information there, we check the photogrammetry data set. Of course, we also are doing evaluation on site while we're capturing. We have visualization, as you saw with the laser arm scanner. We have a live visualization with the structured light scanner. We also have a live visualization. Photogrammetry, you really have to kind of know the process and understand kind of what you have captured and what you should expect the data to look like later, because photogrammetry processing for the most part takes half an hour to a day. So you really don't know what you have until after you're done.
So all that post-processing, how manual or automated is that entire system?
It's pretty manual. Of course, there's automated steps in it, but let's say for every hour of capture, you might be looking at 5 hours of post-processing.
Wow.
So something that we're looking at doing is developing tools to automate more of that process, to kind of automate the data collection and storage, automate the the raw data, what we're getting off the sensors, whether it's the laser arm scanner or photogrammetry, into kind of automating that model creation, and then also creating those derivative models for distribution. So for print, for web viewing, for research. So yeah.
So that would basically make the process of digitizing the other 99% of objects that aren't on view much quicker and more accessible to the public.
Yes, and that's what something we're trying to figure out is how to make a bigger dent in those numbers. Right now 3D digitization is a pretty boutique process, and we're trying to figure out and work with vendors to figure out how to scale it up to the Smithsonian scale.
Well, thank you so much, John. This has been really enlightening for me to see how this all works. And yeah, it was great talking to you all.
Yeah, thanks for coming by.
So Vince, we've seen how all of the data is captured. What then happens with that once it's all been processed and a full model has been created?
Okay, so once we have that 3D scan, we use our Smithsonian 3D viewer. This is a new tool we developed. It's completely open source, so anyone can download this viewer and use it. And we're able to do some things that we can't do in the museum. Like we could spin around the object, we could zoom into different components. But then we could do cooler things, because with this data set, we captured the exterior and the interior. So we have CT data, so I can kind of toggle through the layers.
Whoa.
And now we're looking inside the suit, so seeing some of those components that you would just never see. This was all done using a medical CT scanner. And we can start to investigate this object. So I can click on these little annotations and really just start to learn more about this object. And again, this would be a hard thing to do in the gallery. If nothing replaces like seeing Armstrong's spacesuit, but in terms of interrogating that object more, this is where we think the strengths really are around the 3D model. So we can kind of toggle through all these different layers. I could do other things like take measurements. So if I wanted to turn on the measurement tool, I could click on different areas and actually take accurate measurements of the suit. I could adjust. I could basically cut into the suit and look at different profiles.
This is
so
amazing.
All these things that are really just not possible with the real object are now possible once we have this virtual model.
This is a completely new way to experience historical objects and museums just in general.
Yeah, absolutely. And just the fact that you can think about, we're working with a curator to attach information around this object, but imagine a future where we can connect this content to classrooms around the world, and they could use this platform as a way to teach school kids, put together lesson plans. That's super exciting for us, and that's where we want this to go.
I love that idea.
Yeah, so we're not there yet, but step by step, we're getting there, I think. And the first part was building this tool. And then you could also go to other parts of our website and download the 3D model. So we could basically turn on this AR button, and we could virtually place
there he is.
Neil Armstrong right next to you.
Can I pose with him?
Yeah. So I'm going to get him at the right size. And there we have him. Here he is. That's perfect. Oh, your arm is perfect too. This is great. And then what we could do is take a picture of that.
Whoa, that's awesome.
So that's a really cool way to engage kids, social media platforms, being able to bring these objects out of the museum, out from behind the scenes, into your living room, into your school. It's just super fun. Yeah.
This is so cool. Vince, thank you so much, and thanks for all of the help that your office gave us with Project Egress. It wouldn't have been possible without the scan data.
That's been such an honor.
Thank you.
Thank you, Jen.